Hello, hello. Please comment if I am audible. Thank you. So, welcome to the live session of Pioneer of Success. Today, we will be continuing a COMSOL multiphysics. So, we will be continuing this live session. We'll have multiple sessions where we'll be learning COMSOL multiphysics. So, before starting, I would like to tell something about COMSOL multiphysics. COMSOL multiphysics Physics is basically a simulation tool, or you can say a package that is basically designed for computational fluid dynamics. But not only computational fluid dynamics, it has various aspects of using this particular software, and those are people from electronics background, from computer science background, also from any engineering background. They can use COMSOL multiphysics for their research and other project purposes. So it has wide usage with respect to research as well as other industrial projects. So COMSOL has various applicants starting from this research background people and to the industrial people. So Our purpose is to learn academic purposes of COMSOL, and that's why we are continuing this series. And maybe we'll be having 5 to 6 sessions on COMSOL multiphysics for beginners. And we believe all the sessions will be helpful for people who are learning COMSOL for the first time. So I share my screen. I believe you can see an interface. This is the initial interface of COMSOL multiphysics. So when you open it, you will be getting this window. So what we have to do, we have to make a model and we have to do some simulation. So initially I'll show you the model wizard. So if you click on model wizard, you will be getting this window and you can see there are various options starting from 3D, 2D axisymmetric, 2D, 1D axisymmetry, 1D and 0D. So it depends on the problem statement. If you are working with 2D model, then you have to work with this. If you are working with 3D model, then you have to choose this 3D option, and you also have this axisymmetric option. So axisymmetric means we have an object that has symmetry inside this particular object, and we cut down along the symmetric say symmetric plane, and we reduce the size of the object so that computational cost reduces, and we do simulation with a particular cut section, and then we sum it over to get the entire result for the original geometry. Suppose you have a spherical geometry, so a sphere has a plane of symmetry. So if we cut a sphere, we'll be getting a hemispherical lobe. And if we do a simulation for a hemispherical lobe, and then if we just assume that whatever is happening in the left side of the hemisphere, that will be mimicking in the right side of the hemisphere, then we can do the simulation taking the hemisphere only, and that reduces my computational cost 50% because originally it is a sphere and we are doing the simulation with a particular hemisphere. So 50% reduction of computational cost. So when I call computational cost, that basically means the time which requires for the simulation. So when we are doing simple simulation, then it will not take much of time. But if we do a costly simulation, that means there are many grid points. We have to solve complicated differential equations. Then sometimes a simulation takes say 5 days, 6 days of time. So in that case, reduction of the solution element, the solution element has a huge significance, and that is why our target would be reduction of the solution space as much as possible. So let us go to 2D geometry. For the time being, I am taking a 2D geometry. So what I will do, I'll click on 2D. So those options you'll be seeing once you click on 2D. So what are those? Those are the modules available in COMSOL multiphysics. That means if you have to solve certain electrical problems, then what we should take? We have this AC/DC option. That means alternating current and direct current. If you click on it, you will have several sub options starting from electric fields and currents, magnetic fields, electromagnetic fields, etc. Under this electric field, if I show you, if you click here, you'll get electrostatics and electric current. So there are various options. We have to understand if we are working with a particular physical problem, which module to use to do our simulation. So that idea you should have in order to do simulation with COMSOL. Now one may ask a question like how do we understand which module to be used? To answer this question, I'll suggest that initially we should have a preliminary idea of all the modules, and then some background study in order to understand this COMSOL multiphysics. Once you have this idea, you will understand which module to use for your particular simulation. For say, today I'll be taking a few examples in order to make you aware of how to use COMSOL for your physical problems. But before going into a particular physical problems, let me show you few more options. Like we have acoustics. So people who are working with acoustics, they may have you may use this modules. So for the modules which are available, the simple pressure acoustics, we have aeroacoustics, thermoviscous acoustics. So it depends on which area you are working on. So you choose your module, then go to the module, see the equations, match the equations with your differential equations which you are intent to solve, then decide upon the module which is to be used. We have chemical species transport where reaction mechanism, diffusion mechanism, all those things are there. We have electrochemistry, people who are working with electrochemistry. This module is very much important for that. And then we have fluid flow module, heat transfer module. So you might have come across those terminologies, and you know those terminologies: fluid flow, heat transfer, electrochemistry are important with respect to physics, chemistry, and whatever. So we'll have to understand and we have to choose the physics judiciously. Now I will start with a simple fluid flow problem. So say I go to fluid flow, and under fluid flow you can see there are multiple options, but I prefer to choose single phase flow. So under single phase flow we have various options, say creeping flow and laminar flow. Say now I will be sticking to laminar flow, so I click on laminar flow. Then what I have to do, I have to click on this add. So when I click on add, that means I have chosen this particular physics. So just see what happens if I click on add. When you click on add, this particular module will be added. So this particular physics I want, that's why I have chosen it. Now I will go to study. I click on study. So it will be giving several options for the study. We have stationary and time dependent. There are multiple other other studies, but for this particular case, that is laminar flow, we only have two options, and those options are inbuilt options by default options available in COMSOL. For this particular one, stationary means which is an equilibrium state, that means a steady state that does not depend on time, that is stationary. And time dependent one means unsteady flow, that means that flow nature is changing with respect to time. Suppose I want to solve something which is changing with respect to time. For this particular case, what I will be choosing, I will be choosing time dependent solution. So I click on time dependent. Then yeah, if you double click it, this initial interface of COMSOL multiphysics will come where there are multiple sub windows. So this window is model builder window. From the name itself you can understand that it will help us making our model. This is the setting window where we can change the unit. You can say, you can see this is the unit in meter. I can change this particular unit as per my need, but for the time being, let us keep it to meter. And this is called graphics window. So whatever simulation is happening, whatever result we will be getting, that will plot and we can see in this particular section. That is why this is called graphics module. And those are the tools available to set up your model, to do other calculations, to plot the results and everything like a simple software usually has. So all those things are available here. Now we'll come to the most crucial thing. The first part is geometry. Geometry means we have to define the space, or in simulation term, that is the solution space where we are doing the solution. Suppose we'll be solving a fluid flow problem inside a rectangular channel of dimension somewhere in centimeter, and that's why I changed the unit to centimeter. Now what you have to do, you have to right click on it. You'll be getting several options for making your geometry. As I have mentioned that I'll be working with rectangle, so I go to rectangle, click on it. I'll be getting a particular rectangle option. Now I have to build the rectangle. So what I need to do, I need to define the width and height. So let us consider that the width is 10 and the height is 2 centimeter. Once I define those things, I click on build selected, then I get my geometry, desired geometry. So So today I will not be going to details of all the geometrical options available, but I can tell you, you can make your own geometry. It can be a complicated geometry. So everything you can make here to solve your problem. Apart from that, you can make those geometries in some other CAD software and import that particular file to this COMSOL graphics window. So it has compatibility with CAD files made from AutoCAD, FreeCAD, or whatever software you like to do. But you have to have an extension, say .dxf or some other particular format in order to import that into this system. So we have other videos on this aspect, so you can see those videos, or I'll be focusing on those things in the later part of this particular session. So now I focus on other parts of the simulation. So my geometry is defined. I have the geometry. Now what is flowing inside the geometry? Basically we are solving fluid flow. So a particular fluid should be there. Now I define my fluid. So here is an option, materials. If I right click on it, so you can see there is one add material from library. That means it has a material library. When I talk about material library, that basically means we have several materials enlisted by COMSOL multiphysics, and the physical properties of those particular materials are given, and I take a particular set of physical properties that is pertinent to a particular material. Say I'll be taking water, so I write water and click on search. So what will happen? I'll get several options because in water also there are many options, but I'll be taking liquid water. So I look for it. So you can see here something water liquid is there. I click on it. Either I can click on add to components, or I can double click on it. If I double click on it, this material will come. And as I have mentioned, material means in terms of simulation, material means a set of physical parameters that water has. So what are those parameters, and what are the parameters useful for doing this simulation? Those are basically density and viscosity. But if you solve temperature dependent, then you may require this thermal expansion coefficient, heat capacity, and all those things. But today I'll be working with a simple file, so I will be needing density and dynamic viscosity. So you can see these check options are there. That means it is taking the values from the system. That means this material. So and another thing is very much important. So you can see now this is selected by blue line. If I click on it, you can see I have deselected it, and you will be seeing one cross sign here. That means yet material is not selected in the system or in the solution space. So whenever you do simulation, you have to make sure some material is there. Otherwise, it will not get the physical parameters, so it will not be able to do your calculations. That's why we should ensure that the material is selected at appropriate place. Then I go to, so up to this point, whatever happened, I just recapitulate. So geometry selection is done. I have selected material inside the solution space. Now I go to the original thing, that is the equation which I intend to solve. So this is laminar flow, this is the equations which we solve are continuity equation and the momentum equation. So for the time being, if you even do not understand those equations properly, but you understand this, that for solving fluid flow we require these two equations, and those two equations are available in the module. So when we choose this laminar flow, it automatically takes these two equations, and those two equations are basically required for solving fluid flow. Now, what we have to do, we know that for solving a particular physical problem, that basically means we have to solve a few differential equations, and most of the time, those differential equations are partial differential equations, and so are here. All the equations are partial differential equations, and we require appropriate boundary conditions in order to solve a particular physical problem. So, we should define our boundary condition in this physics. So let us define our boundary conditions initially. So we right click on it. There is one option inlet. We click on it. Again, we right click on it. Another option is there outlet. So we have taken our inlet. That means water will come from a certain point, which we call as inlet. So now the inlet is not defined. So I have to choose this left part is my inlet. When I put my cursor here, it shows a red line. Then I click on it, it will become blue. That means this part is selected. And what is happening at the inlet, that I have to define here. Suppose I define certain pressure at the inlet. So the pressure is 100 pascal at the inlet, and outlet is the rightmost part. So this is the outlet. I define this outlet and I keep pressure equal to zero at the outlet. Here pressure zero means this is the gauge pressure. That means excess of atmospheric pressure. Basically, this point is at atmospheric pressure. That's why we are putting zero. And this point is at some elevated pressure, that is 100 pascal, and we define it. So those two boundary conditions are defined, and automatically there was some option wall. So these two are walls, and at walls, what we define, this is no slip boundary condition. What does it mean? At this point, the velocity component, that is u and v, both are zero. Both are zero. I mean, we have defined zero. So all the boundary conditions are now set. Now, there is one option fluid properties. Now, where from it is taking the fluid properties, that is important. So, if you see here, it is asking for two parameters, and those are rho and mu, and something is written over here, and that is from material. That means we have chosen an appropriate material inside the solution domain, and it actually requires those two values, and it is taking the values from the material because we have defined the material and all the parameters are enlisted in the material. So the problem of defining rho and mu is over. Why do we require rho and mu? If you see the equations appropriately, there are parameters rho, and there is one parameter mu. So those two things are required, and it is taking from the material. So now I can say my problem is properly defined, and I can proceed with the simulation. And numerical simulation means what we'll do is we'll discretize the solution space, we'll cut down into several grid points, and we'll be solving the differential equation at those grid points. Before that, it will discretize, it will convert the differential equation to algebraic equations, and it will solve for all the algebraic equation, and it will give the values to the user. So now the important part is meshing. So we click on okay, so there are several kinds of meshes available. There are some inbuilt options. So whenever we learn some simulation or any device, if we want to use, so what we prefer to go with the default options initially. Once we become familiar with the device, with the software, then we click on several parts, we learn the software and go ahead. And similarly here also, whatever is defined by default, we'll be sticking to this, and this is normal size mesh element, and we stick to this, and we click on build all. So it will be building the meshes. So those are the grid points where it will be solving the equation. So up to this point, geometry is done, material selection is done, problem statement, equations, boundary conditions are done, and then meshing is also done. So the ultimate step is pending, and that is solving the particular equation. So you can see there is one option study, time dependent is chosen. By default we are solving from 0 to 1 second with an interval of 0.1 second. So whatever solution will come, it will be storing the data at interval of 0.1, 0.1, 0.1, and it will go up to 1 second. So let us stick to the, the default definition, that is 0 to 1 second, and let us do the simulation. How to do the simulation? We have to click on compute, and it will start the simulation. So I'm just clicking on compute. You will see the simulation will start shortly. Yeah, you can see the progress of the simulation from here. It has started, and Yeah, the simulation is completed. So this is a simple simulation. That's why it takes a few seconds to run. But when we deal with multiple equations, complicated geometries, several meshes, then it takes more time. But to learn with, to learn the software, we'll be sticking to simple problems which will hardly take few seconds to run. So here we have simulated, and you all know where this is basically a pressure driven flow. So what happens in a pressure driven flow, this is the profile or contour. I we have defined no slip conditions at the walls, and that's why the speed is zero here. So the blue color, that is the response, I mean, that shows zero velocity, and at the middle the velocity is maximum. So if you just click on any point on it, it will show the velocity. You can see it is showing something 0.92046. If we move towards the wall, the velocity will go down. Let us check it. Again, we click somewhere. You can see the velocity is going down. It is becoming 0.795 or something. So this is how the fluid is moving inside the pipe. So we have solved the particular physical problem. So let us stop here today. If you have any query, you can just write in the comment box, and I'll be taking your comments one by one. Yeah, somebody commented, your video on FSI was very good. Good job. Thank you. I tried your FSI simulation with some twist, but I ran into problem when the solid moves towards wall. The solution does not converge. Maybe your velocity of the object which is moving, that might be very high. That is not compatible with the solution. I mean, feasible. That is not feasible. That's why maybe these things do not work. So you can try with other possible velocities of your object. It may work. So I'll wait for your comments if you have any comment. Yeah, I can understand that velocity is coupled with fluid flow, but still, how much velocity you are putting, the object is taking, that is important. But we'll have separate session on fluid structure interaction. We'll be continuing this session. So you'll be getting updates when I'll be doing this live session. You can join, and I will can discuss over it. Yeah, Rick, thank you. If you have any question, you can put it in the comment box. Rick, Arnav, Manas. Yeah, this equation can be used for any kind of fluid. Only the fluid properties we have to define. If this is, say, Newtonian fluid, so we have to define the Newtonian property. If this is non-Newtonian, then we have to change the viscosity and we have to put some function. And there are models for that. We can, but the answer to your question is we can work with any kind of fluid with this equation. I'll wait for few more minutes. And the most important thing is we'll be continuing this session, and maybe we'll be having one or two live sessions in a week, or in an interval of 2 weeks. We'll be having this, and we'll be continuing for a few months, maybe 3 4 months from now. Can you hear me? Can the solid object be bounced off the wall during exercise simulation? No, this is not possible. If you are looking for this kind of problems, then you have to look for other physics and fluid particle interaction. This is not fluid particle interaction. There is FPT, that is flow of particles in fluid flow. One FPT module is there. You can try that module if you want bouncing problem. But for fluid structure interaction, when the object hits the wall, then remeshing becomes very difficult and your solution will diverge. It will stop actually. So today I'll end this session. Maybe after a week we'll again meet, and we hope we will smoothly continue this session. And thank you very much for joining this session. So I'm just signing off for the day.